So now I will go to chilled water system. So, like I mentioned just now, chilled water system, there's an additional loop. And this additional loop, right, okay, is called the chilled water loop. So what happened is, the whole of this vapor compression cycle is housed inside this piece of device which you commonly hear is called chiller. So your vapor compression cycle, okay, the whole of this device, right, is under a single unit, okay, and this whole single unit is what we call a chiller. So let's say now I use a box to represent chiller, okay. What happened is there will be two loops, okay. So you have one loop, and this loop, right, is providing chilled water, okay. So chilled water will go in at certain temperature and come out with a much colder temperature, okay. So let's say the water go in at around 13 degrees Celsius, come out at around 7 degrees Celsius, and this part is the evaporator that is cooling your water. So now actually there's this additional water loop that's flowing around, and of course ultimately it may flow into your AHU and FCU. AHU is what we call an air handling unit. So now the thing is, at the condenser side, we know that this region is the condenser and it's very hot, and you have to remove heat from the condenser. So there are two ways to remove heat from the condenser. It can be either by air or by water. If you remove heat from the condenser by air, this chiller is called a air-cooled chiller. Air-cooled chiller. If you remove the heat using a water, that is called a water-cooled chiller. So now let's look at air-cooled chiller first. So air-cooled chiller, at the chiller's side, okay, there are a lot of fans. There are a lot of fans to actually remove heat from the condenser. So you can see that at the condenser side, the condenser is actually being cooled down by ambient air. Okay? And if we refer to the schematic that we used just now, now there will be an additional chilled water loop. Okay, you will notice there's additional chilled water loop from the evaporator to the AHU and FCU. Okay, so you can have multiple AHU, you can have multiple FCU inside the building. And the cold water will be cooling down your air. Okay, it will be cooling down the space. So if you look at the temperature reference, okay, you will notice that now there's this additional chilled water loop. Okay, so you use a 7 degrees Celsius water to go and cool down the space, cool down your air. Okay, and your refrigerant must be even, will have to be even lower temperature. Okay, so just now you notice that for DX system, the temperature is around 10 degrees Celsius. But if you are using a chiller, the refrigerant must be around maybe 4 or 5 degrees Celsius in order to supply a water of 7 degrees Celsius. Okay, so that is the reason why the refrigerant temperature is much lower, because you have an additional loop. Okay, now I will talk about the most common type of cooling system in a building, that is using a water-cooled chiller. Why is it the most common? Because it's suitable to use for large buildings with multiple stories, or even multiple buildings can share a single chiller plant. So the most common type of cooling system is using a water-cooled chiller. Why is it called a water-cooled chiller? Okay, so just now we have learned this air-cooled chiller. Okay, we have learned this air-cooled chiller. So what it does is to provide chilled water to your AHU and FCU. Okay, so the difference between air-cooled chiller and water-cooled chiller is at the condenser side. So for air-cooled chiller, your condenser is being cooled down by air. As for water-cooled chiller, your condenser is being cooled down by an additional loop, and we call this the condenser water loop. So your condenser is being cooled down by water, and after your water gain heat from the condenser, it must be rejected somewhere. And that is when you are going to use this additional so-called equipment, which is called a cooling tower. So cooling tower is effectively a tower with water that's being dripped down. Okay, that's been trying to spread out the water, and at the same time you have some fans, okay, below that's blowing across all this water. So what it's trying to do is using evaporation of the water to cool down this condenser water. So the condenser water temperature that's going in may be around 34 degrees Celsius. Okay, so after passing through the condenser water, the temperature will drop by maybe around 5 degrees Celsius to 29. So this temperature will be much cooler than the condenser. That's why it can remove heat from the condenser, and at the same time it gets heated up itself. Okay. So now you see, now there's an additional loop on top with an additional component called the cooling tower. Okay, so at the cooling tower, right, okay, the water, like I mentioned just now, is getting warmer because of the condenser that is rejecting heat to it. Okay, so the condenser water get heated up to 34. It will so-called trickle down the temperature. Okay, trickle down the tower, and you have a fan to induce evaporation. That's how it brings down the temperature of the condenser water. So water-cooled chiller is very commonly used because it has a better COP. Okay, it has a better coefficient of performance. It is much more energy efficient, although you will need more capital cost because there's additional equipment. So if you look back at this same diagram, you will notice that now at the hot refrigerant side, you have an additional loop, or additional agent that is called condenser water. Okay, that goes in at around 29, leave at around 34. Okay, so notice that the entering condenser water, which is the water that leaves the cooling tower, will be near the wet bulb temperature of the outdoor air, but it can never be lower than the wet bulb temperature. So that is to say, let's say the ambience wet bulb temperature is around 28 degrees Celsius. The water temperature that comes out from the cooling tower, the lowest it can get is 28. It cannot go below 28. So usually there will be some gap. Okay, so the gap, we call it approach temperature. So for example, the water temperature that comes out is around 29. You have an approach temperature of 1 degree Celsius. So why is the COP of water-cooled chiller much better than air-cooled one? So if you notice, if you use air to cool down the condenser compared to using water, definitely water will be able to cool down the condenser to a lower temperature. So if the condenser is being cooled down to a lower temperature, what will happen? If we refer back to our first topic, at the condenser side, with a lower condensing temperature, the pressure will actually reduce. The discharge pressure of the vapor compression cycle will actually reduce. So your compressor will be using less energy because there's a smaller delta P. So the difference in pressure, you have this trapezium shaped thing. Okay, the difference in pressure over here, we call it pressure head. So if the pressure head is low, your compressor don't have to work so hard to bring it to this pressure. So the flatter is the of this shape, the flatter it is, the better it is. So if this line is able to shift downwards because of lower condensing temperature, you will have a better COP. So just now I mentioned about this thing called the wet bulb temperature. It's actually closely related to the humidity of the ambience air. So let's say the humidity is now very, very high. What will happen? if the humidity is very high, the wet bulb temperature will be also very high. Okay, it will be near to your dry bulb temperature. So what happens is, the water, let's say your wet bulb temperature is not 28. During a rainy day, it can be up to, let's say, 30 degrees Celsius. So if the wet bulb temperature is 30 degrees Celsius, the water that comes out from the cooling tower cannot be at 29 anymore. The lowest it can get is 30, or maybe even 31 degrees Celsius. So if this temperature that is 2 degrees Celsius higher is being used to cool down the condenser, the heat transfer may not be so effective compared to when it's at 29. So the higher is your the temperature that is coming out from the cooling tower, the less efficient it is in removing heat from the condenser. And using the same argument, your line now will be shifted upwards. You will have a higher condensing temperature. And because of that, your pressure head may increase. Your pressure head may increase. That will cause your compressor to work harder. And therefore, your COP will suffer because of that. So, that is the reason why during a humid day, your COP is actually being affected by the high temperature that comes out from the cooling tower. So now let's look at a typical chilled water system configuration. So what I have mentioned just now is all belong to what we call a water side. So this one is the condenser water loop. Okay, and this one is your chilled water loop. Chilled water. So for these two loops, you have we classify them as the water side. And after the AHU, we classify them as the air side. The air side of the ACMV equipments. So for air side, we have AHU and FCU, which stands for air handling unit and fan coil unit. So both of these components, both of these equipment, right, they have the same things inside. Okay, they have fan, they have cooling coil and air filter. Okay, and of course, if you have an AHU, most of the time you will have air duct, the air duct that will transport the cold air around. Okay, as well as some other duct components such as your dampers, your VAV box, etc. For the water side, it's very clear cut. Okay, you will have your chiller. Okay, you will have your cooling tower, as well as the pumps that are being used. The pumps that are being used to transport the water around. So you have two types of pumps. One is the chilled water pump that is being used to transport the chilled water around, and you will have your condenser water pump that is transporting the condenser water to the cooling tower. So all these equipments in a real building, okay, doesn't mean they have to be 1:1. Okay, what I'm trying to say here is, let's say you have one chiller inside a building, doesn't mean you can only have one cooling tower and one AHU. Okay, so a typical chilled water system configuration, right, you may have 3 or 4 chillers, and you may have 3 or 4 cooling towers or even more. Then AHU can have up to 10 to 15, and FCU can be up to 20 to 40. Okay, so all this, it depends on the amount of heat you need to remove from the buildings. Okay, so let's look at this diagram and try to label all the terms that we have just learned. Okay, all the different kind of components in this air conditioning system configuration. Okay, first we have AHU, which are the 3 so-called yellow boxes. Okay, so usually one level, right, you will have one or two AHU. Okay, it depends how big is your floor area lah. Okay, so let's say you have a 10-story building, you may have 10 to 15 AHU to cool down the entire space. Okay, then some of the spaces that is not being cooled down by AHU, it may be cooled down by FCU. For example, those small localized area like your pantry or your server room. Okay, all those may be cooled down by FCU instead. Okay, next we have the cooling tower on top. Okay, as well as the chiller below. So it depends. Some of the chillers are at level 1, Some of the chillers are at near to the rooftop. But most of the time, chillers are at lower level or even at the basement area. Okay? And remember, this chiller itself actually consists of the vapor compression cycle. So vapor compression cycle, we have two very important components, which is condenser and evaporator. So condenser tube and evaporator tube, okay, is part of this chiller. So CHWP is usually used to represent chilled water pump. So chilled water pump, of course, the use is to transport your chilled water around the building to all the different AHU. And one thing to take note is, usually your pumps is transporting water towards the chiller. So you may notice that the chilled water pump is pumping towards the chiller and not away from the chiller. So primary pump is always towards the chiller. So usually chilled water pipes are being labeled with blue colors. Okay, they are blue colors. And you may have noticed the chilled water pipes sometimes is differentiated into light blue colors and dark blue color. So usually the light blue color represents chilled water supply temperature, chilled water supply water, and dark blue color is chilled water return. Okay, so of course the darker color one is usually the higher temperature water. Okay, so chilled water return is higher temperature, that's why it's dark blue color. And on the other side, the condenser water loop, okay, you have your condenser water pump, and you notice that it's also pumping towards the chiller. And you have two pipes, okay, one is the condenser water supply that is coming out from the cooling tower and going into your chiller. And that's what we call condenser water supply. So it's a bit misleading when we use the word condenser water supply, because it's supplied towards the chiller and not like the chilled water. Chilled water, when we say supply, is supply from the chiller. So if to prevent confusion, sometimes I will use the term called ECW, or entering condenser water. Then you'll be very clear. So entering condenser water means the water that enter the condenser. Okay. Similarly, LCW will be leaving condenser water or condenser water return. So for condenser water pipes, usually they are in green color. Green color. So light green is condenser water supply, which is the lower temperature one, and dark green is your condenser water return, which is the higher temperature water that is going to your cooling tower. So this is a typical water system configuration. And if you are familiar with the building management system, in short the BMS, most of the time the BMS will have one schematic that will represent what is happening, okay, at the chiller plant site. So usually this schematic will show you how many chillers you have. In this case, there are 3 chillers, okay, and how many cooling towers. Here there are 3 cooling towers and the respective pumps, okay. So a BMS is used to monitor what are the parameters, for example the temperature, for example the flow, and the status of the equipment, whether is it on or off currently. So if you look at this particular schematic, you will notice that chiller 1, which is represented by CH01, okay, is on because it's green color, whereas the other 2 chillers are off. So you notice the temperature, all this, it makes more sense. The chilled water supply temperature, if you notice, is around 6.72 degrees Celsius. The return temperature is around 13. Okay, so from the schematic, you can also get an idea of the whole chiller plant configuration. So of course, it's impossible to put all the AHU readings, all the temperature of your air into one single page. So usually BMS, there are multiple pages, usually differentiated into different AHU. For example, AHU 1-1 will have, you will see all the temperature readings, all the parameters inside AHU 1-1. Then you may have AHU 1-2, 2-1, etc. So that's how how this system is being seated at the FCC, and a person can just sit there and monitor the whole chilled water system configuration from a single location.